Hey there, it's Max. This is the House of Force module exercise 1 solution. In this, we're going to use the House of Force to exploit a fairly standard buffer overflow-like bug. So I hope you guys actually went through and did this. I think this is a pretty good time. And hope you guys played around with this, messed around with GDB, try different strategies for using it. I think it's really fun. So with that, we're going to do like we normally do. We're going to talk about how to solve this abstractly. We're going to solve this live and manipulate some stuff in Python and GDB, and then we'll wrap it up by going through this visually. So the first input we have is the corrupting the top chunk. And right now, they're just hex zeros. That's it. But we just want this to be very, very large. So just by setting this to be hex FF, the top chunk is gigantic, and we get exactly what we want. So that's the first input. The second input is the size. And I was pretty nice with comments. And I calculated some stuff for you. So the size here is going to be size minus hex 10. Minus hex 10 because we need to do that minus 20 to account for the two chunks metadata. But our target here is going to be the malloc hook. And I've already done the math here for you with libc base, but we can do this by hand again as well, just for fun. So the actual size of this is going to be the malloc hook minus top chunk location. And that happens to be the same as the heap base, but any other situation it probably wouldn't be. So this is going to move the needle, relatively speaking, from the top chunk to really, really close to the malloc hook. And then once we do the code exec here, we pop a shell, we win, get the dopamine hit, yay. So before we actually write this, I think it's kind of fun debugging and seeing what happens if we do this incorrectly as well. So I think setting this to hex FFF is interesting to look at in GDB, so we'll start with that. Of course, that is my local copy, so it doesn't help me very much. I always forget that. So I'm just going to change the size here real fast. If I could type normally, that would be great too. So now we've actually done this overwrite. I think that's where this first breakpoint comes in. No, we have not done the overwrite yet. Okay. So we go to the next breakpoint. And now if we look at top chunk, you'll notice that it's virtually infinite in size. So this chunk, we've definitely written the size of the top chunk. That's the first part to this exploit. So if we continue, it exits normally because we're not really doing anything too interesting in terms of allocations, in terms of the size of those allocations down here. So not a huge deal at that point. We're probably just taking some memory from the top chunk. Now if we do something a little bit more interesting, because this one's just doing size. But if we do something more interesting, then we can cause some havoc. So for instance, if I do something like this, and then try to execute it, I feel like this will probably crash when it tries to do that allocation. Yeah. So you can see that we're in int malloc and it stopped. And it actually froze at this set head function. So the set head is going to be setting information about the pointer here. It's setting the remainder size and preven use bit, which is setting the top chunk information. But if we look where it crashed at, we can see it's EAX plus 6. If we just look at that, that's not an actual address. So that's where the problem arises from. We gave it a chunk size that it thought it could go into, but when it actually tried setting that value, poof, it crashes. So this is when the actual calculations for the real thing come in. So again, that whole moving the needle principle, and I'll show this in slides in a moment, but it's going to be malloc hook minus top chunk. It's like if you're doing math about how close you are to something, you don't think about the point zero on a map. You think about where am I relatively speaking. So if I'm trying to walk from Seattle to New York, you don't go, what's grid zero? You think, okay, I'm already at this point, not the zero address. I'm already partway into this address space or partway into the geographical location. How close am I to this? And so you're just doing some offset math in order to figure that out. So that when you know, so now you can calculate how close you are to it and how far you need to go from there. It's the same thing, but with this. We're just moving the needle and we're doing relative offset math. The 2 minus 10s here, this is for the chunk that's going to become extraordinarily large, the filler chunk per se. That's that metadata. And then the next hex 10 is for the second or overlapping allocation, because we want to make sure that we actually get to overwrite the data we're touching. So now if we do Python 3 start.py and we do continue, oop, I did something wrong on my Python script. Is it not top chunk? Top chunk loc, that's why. Cool, so now if we try this and we continue, my Python script should work this time. Okay, now if we do continue, the place in which we've stopped at is right after that third malloc, or right before that third malloc allocation. That's interesting because the chunk second is going to be the very large one. The chunk third is going to be over our target. So if we do top chunk, we can see that this address is going to be in libc. We can look at vmmap and see that this is definitely going to be a libc address. And more importantly, if you do print underscore malloc hook, and we print the address of that, we can see that 7F63, 7X63CB, we're right there. And that's the cool part. If we look at the code that we were just looking at, I think it was a chunk called second. If we do chunk second, and we do I don't know, address minus hex 10. I did that wrong. Yeah, there we go. Okay. So we're looking at the address of the chunk second, and it starts with just this 204D, but we can see the size is ludicrously large. So this definitely indicates that we have gone, we've exploited the House of Fours technique to allocate an arbitrary distance in memory. So I think that's pretty cool as well. So now if we do next and we print the address of the chunk third, it now, whoa, I don't know how I did that in tmux, but that's okay. So here we can see that the chunk third is what we're allocating over. And now we're going to do the call to fgets, and that's going to be over the top of our thing. And now we pop a shell, which is cool. So now we can do who am I and ls and all of that fun stuff. Root. Okay, cool. Got the dopamine hit now. Let's go. In the solution.py file, I have the same thing as well. In this case, we use the malloc hook, but we can also use the got entry for puts. And I have calc size puts in the solution here. I think this one's kind of funny because you literally wrap around. So it just looks really funky when you do this. So instead of, this looks kind of weird because it ends up being like a negative number, I think, um, compared to the other one, because you're literally wrapping around the address space when you do this, which is another really funny quirk about it. So that is the House of Force done using our little setup script and you playing around with it. I hope you mess around in GDB a good amount as well, 'cause I think it helps with intuitive understanding, just seeing the numbers and how stuff changes. Now we can go back to the slides though. So as we recall, we need to corrupt, allocate, and overlap. I'm going to cut up a pen because I'm probably going to need that. So the first step is the corrupting. In our case, the corruption is pretty easy. The chunk first points here, but then we write to minus hex 10. So by overwriting the information in the top chunk, we can cause some really bad habit by extending that. And that minus hex 10 to overwrite the size is the thing that causes the problem. Now, we want to set this to just be some value. You can write it with A's, you can write it with B's, you can write it with whatever you want. But I just like writing it with -1 or all F's. And the reason is, there may be a situation down the road where I need to have it wrap or be at a very specific value. And by setting this to be the biggest possible value, I can do whatever I want with it. And I really like that. I don't have to think about this ever again, and that's really nice. Also, the proof size doesn't really matter. All right, so the second thing we need to do is we need to allocate. For the allocation step, we need to allocate a large section that lands directly in front of the target. In our case, that is the malloc hook. This is the code that's there. We control the size of an allocation that is going to be done. And that's exactly what we need for the House of Force. So we have the location that we want to write to. We have the arbitrary size allocation. Now we just need to figure out how to actually calculate the location to the malloc hook. So I'm going to turn off my camera again. Like we said before, we've now corrupted this top chunk, and there's this gap here. Now we want to write to this libc address, and which is going to be the malloc hook. So the general idea is that we need to somehow move that needle close enough to the target so that the next allocation will be directly in front of it. Now, this size can be calculated just by thinking about that relative math, the geography example I gave before. When you're driving, you think relatively how close I am. This is the exact same thing with this as well. So in this case, we're going to take the address of the malloc hook, the address of the top chunk, and do an additional minus hex 20 in order to account for the metadata information. So if we use that size, then when we actually do the allocation, we get really close to our target. That's all we want. So a more compact picture of this now is we have the heap in libc, and the top chunk is pointing somewhere in libc, but the malloc hook is a little bit further below it. So all we have to do is one more allocation, and we should be good. You could also choose other targets. You could do the God entry for puts, the stack return address, but just for explanation, I'm just going to share the one. So for the overlapping step, this is the easy one. Now that our top chunk thinks that it owns this memory space, if we just do one more allocation, now our target thinks that it's over the top of the fake chunk, over the top of the malloc hook, and we've placed our fake chunk there. The top chunk goes down a little bit more, thinks it owns different space, but now all we have to do is write to that. We can write the address of pop shell, and it pops a shell, which is really exciting. So I hope you guys enjoyed that technique. Again, just one of my personal favorites. Just to recap, we corrupt the top chunk size, we allocate over the top of it, and then we overlap with our target after that. So the one drawback to this, though, is that it was patched in 2.29. I can't believe it took this much time to do that, but around this time period, the maintainers of libc decided that these techniques were becoming more widespread, were becoming a bigger issue, and so a lot of issues in tech exploit methods like this did get patched. It's funny though because it's not really the allocator's fault. Like, you are misbehaving by allowing for buffer overflow in the first place. So I think it was fair to not have these in the past, but heap exploitation became more popular, it's being used in more things. It's not too big of a memory hit, so they just started adding this. And the check just makes sure that the AV system mem, which is a entirely different variable, is like the entire. I think that's the entire section of the SBRK allocation. It's not just the leftover of it. It just makes sure that the size is less than that. So you can't go. You can go out of bounds on it, but you can't go far enough out of bounds where it's actually very useful. There's also the other drawbacks to this is that there's arbitrary size allocations like this are hard to come by. Most of the time they're sanity checks. It also requires a heap leak or a heap leak and a leak to your target, which is difficult. And you also have to corrupt the top chunk, which may not be possible in all situations. My final thought is, I think it was Kevin Backhouse also has a really cool article where he used a variant of the House of Force to exploit some bug in Linux. I'll link that in the slides as well, but that's actually like a real world exploit that was used this technique. I think it's pretty fun to read about. So I hope you can use the Force. Now, I think this is a really cool primitive. I think it's a really fun technique. So I hope you enjoyed it as much as I did. Thanks. See you in the next module.